All right, hello Algebra 1 Honors. Today we're going to look at section 5.4 and it's titled Solving Special Systems of Linear Equations. And we've had a little bit of experience with systems of equations already. We've learned how to solve them by graphing, by using algebra, using elimination and substitution. And today we're going to look at special situations. And so what I'd like for you to do is in this big space here, I want you to kind of draw a grid. Draw a little line across the top. And then across the top, I want you to write, let's get to that here in a second. Let's draw a vertical line down the side with a little bit of space there. And then, yes, draw another one, split it up into some columns here. There we go. Okay. So what I want to examine is I want to examine what these special cases look like when we have a graph, when we try to solve them by graphing. And then I also want to look at what these special cases look like when we are using algebra. So with substitution and elimination. All right, so I think, actually I probably had a little too much space down there. You know what, I'm gonna take care of it right now. I'm gonna need some of that space there, so I'm just gonna use my oops tape here, clean that up a little bit. Oh yeah, there we go. Oops. There we are. All right. So there's three possibilities or three types of solutions that you can have with linear systems. And one possibility is that it works out normal and you get one solution. Now let me be clear on this. That one solution is a coordinate. It's an X and a Y value. So another thing that can possibly happen is that you might get no solution with a system of equations, okay? And then finally, a third possibility is that you might have infinitely many solutions. Infinitely many solutions. Okay, so graphically, what happens when we would graph these and we would get an answer? Well, they would, you'd graph one equation, you'd graph the other, and lo and behold, you would get a coordinate in the middle there where they overlap, and yeah, your one solution would be that coordinate, that X and Y. So with graphs, what would happen for no solution? I believe we maybe talked about this, but think about what kind of situation would be where they don't cross, and you pretty quickly realize, oh yeah, parallel lines. If you graph them and they're parallel, then you're going to get no solution. No solution as soon as you realize that they're parallel. Oh, and by the way, there's some notation. If you put an extra set of arrows on some lines, it tells the world that those are intended to be parallel. And then the other option is infinitely many solutions. And when that happens, it happens that you graph one and then you graph another and they're right on top of each other. They're the same line. And when that happens, notice the slope will be the same, but so will the y-intercept. Everything will be the same about them. And so if that's the case, you're going to write infinitely many solutions. Infinitely many solutions. Now with algebra, doing algebra to solve systems of equations, You're either going to do substitution or elimination. And when you get one solution, you're going to work it out and you're going to get one variable solved for, and then you keep working and you get the other variable solved for. And together those form the one solution. They make a coordinate of -3, 4. Well, for no solution, what happens with substitution and elimination is that the variables will go away completely. The variables will go away completely, and you'll be left with a false statement. So you'll just be working it along. You'll do your substitution, your elimination. You'll work it out, and the x's and the y's go away, and you're left with something like 8 = 5. Or more commonly, you'll get like a 0 for one of the values, so like 0 = 3. Well, are those statements true? No, they're not. Those are false. So if you have a false, if the variables drop out and you're left with a false statement, that's going to mean no solution. And the last option there, infinitely many solutions. Same thing. The variables will go away completely. But this time, you're going to be left with something like 5 = 5. Or what's common is you'll get 0 = 0. And you'll be left with a true statement. So the variables eliminate or add or subtract, and they're gone. And so you're left with the true statement, and in that case, you'll write infinitely many solutions. All right, so let's do a couple examples here with graphing. So our first example, we're going to solve by graphing. And let's do a system of 5x plus 3y = 6 and -5x minus 3y = 3. And these are actually written in standard form. One way that you could graph these is by using intercepts, and it's not a bad way of doing it. Except for I don't think the intercepts are super nice. But another way you can solve these is by getting them in slope-intercept form. So we'll get y by itself. We'll subtract 5x over. Get 3y = -5x plus 6. Divide everything by 3. And we get y = -5/3 x plus 2. And go ahead and graph that. If you've got a straight edge handy, it's a good idea to use that. Down 5/3. You can back it up. Up 5, back 3. And I'm looking for my straight edge. It's around here somewhere. I just know it is. Oh, there it is. Okay, cool. Use your straight edge and graph a line. And try to fill up the page as best you can. And then let's go and work on our second equation. I'm going to add the 5x over, so I'll get -3y = 5x plus 3. Divide everything by -3, divide everything by -3, and this time I get a slope of -5/3, and then we got the x, and then the y-intercept of -1. So I'll go to -1. Oh yeah, and look at that, same slope, isn't it? You can either go down 5 over 3, or if you want, you can go up 5 and back 3. But then take a look at what you got here. Are these lines going to intersect? Not with the same slope, they're not. So parallel, yay. And that means no solution. Now, I'll be honest, you could, once you've gotten y by itself, looked at the y-intercepts, saw that they're different, saw that the slopes were the same, and you could have come to that same conclusion without graphing. But here's the thing, if the instructions say solve by graphing, by golly, you better graph it. Well, let's look at a second example. 4x minus 2y equals 8. Y equals 2x minus 4. And to graph this first one, we could graph using intercepts, which, I don't know, let's do that. That might be kind of fun, actually. The x-intercept is found when y's value is 0. So you're going to get 4x equals 8, or x equals 2. The y-intercept is found when x's value is 0 and divide by -2, and you're going to get a y-intercept of -4. And so we can actually graph that line using the intercept. So we'll put a dot at the x-intercept of 2 and the y-intercept at -4. Now, after doing that, you can see that there is a slope that exists there. You could go up 4 over 2, up 4 over 2, up 4 over 2, down 4, back 2, to get you more equations on the line. And there we have it. For our other equation, it's in slope-intercept form, so we can go ahead and go down 4. Oh, wait a second, look, that's an intersection point, isn't it? Down 4, y-intercept of -4. And then our slope is up 2 over 1. Up 2 over 1, up 2 over 1. What have we discovered? Well, we've discovered that they're the same line. And so what I'm going to do is I'm going to put an extra set of arrows going both directions there to make it look like I graphed two lines. And when they're the same line, that means every single answer on one line is a solution on the other line. So that means there's infinitely many solutions. Infinitely many solutions. All right, flip this over, see what else we got. Well, we don't have anything, do we? Now let's use algebra. So solve using substitution or elimination. And for our first example, remember these are often given to us stacked, so I guess I'll go ahead and stack it. No, I'm not. I'm going to save some time. They're usually given to you stacked, but you want to write them side by side to make everything flow a little better. But 2x minus 3y equals 6 is our first equation. Our second equation is 6x minus 9y equals negative 12. So looking at this problem, you certainly could solve it by substitution, but there's not really one variable that really sticks out as being a super simple one to get by itself, I'd probably get the x by itself. It might be a little bit easier. But when there's no x or y that's all alone without a coefficient, I'm kind of thinking that elimination might be a better way to go. Also, these are both written in standard form, so I'm going to go ahead and do this using elimination. I'm going to put 6x minus 9y equals negative 12, stack it. Also, I should mention, some people also call elimination linear combinations. All right, so the goal with elimination is you want to add or subtract these equations together so that one of the variables goes away, allowing you to solve for the other variable. Well, in this case, if I added these up, nothing would go away, but I can remedy that by multiplying this top equation by what? Let's see, it looks like I can multiply it by a negative 3 to get the x's to eliminate. So we got to multiply everything by a negative 3. So I'm going to rewrite both of them down below here. So I'm going to get negative 6x plus 9y equals negative 18. And my other equation was 6x minus 9y equals negative 12. And my x's eliminate, but my y's also eliminate. So is there anything left on this side? Well, a 0. Yeah, nothing's left, so 0. And on the other side, I get negative 18 minus 12 is negative 30. So here's the thing. The variables went away. Both of the variables are gone, and I'm left with the relationship here. Is it true? Is 0 equal to negative 30? No, that's false. So what's our answer? No solution. So as it turns out, if I was to have solved for y, or if I was to have graphed these, I would notice that their y-intercepts would be different, their slopes would be the same. All right, let's try another one. Y equals 2x minus 4 and negative 6x plus 3y equals negative 12. Since one of the variables is already solved for, I'm going to go ahead and use substitution here. I'm going to take that 2x minus 4, substitute it in for y, and go ahead and work this thing out. Combine like terms. Oh, interesting. The x's go away. I get negative 12 equals negative 12. Well, the variables both went away, didn't they? But in this case, I'm left with a true statement. This is true. Negative 12 is equal to negative 12. Sorry. Since it's true, this is a special case. And in this case, since it's true, we're going to say infinitely many solutions. All right. And sorry, I'm getting some texts here from my family. My son, he wants a new jacket. That kid, I tell you what, he likes his jackets. Our last example, let's take a look. X minus 3y equals negative 9. X minus y equals negative 1. Substitution or elimination, either one's going to be pretty easy. I'm going to go ahead and do, elimination. I'm going to write 1 underneath the other. X minus y equals negative 1. Right now, if I added them up, they would not eliminate. So I am going to multiply the bottom one by a negative, or you can think of it as subtracting everything. If you subtract a negative, though, you add the opposite. So it's going to be plus, plus. And then let's see what's left. Is everything going to go away? No, we're going to get a negative 2y equals negative 8. We're going to go ahead and be able to solve this, aren't we? Y is equal to 4. And then once we get y is equal to 4, we can take it over here, substitute it again, solve sub. Well, actually, this isn't solve sub because we're not doing substitution. But anyway, so we get to substitute here. And we can solve this. So add 3 over, add 4 over, we'll get 3, ahead of myself a little bit, and we get an answer of 3, 4. So what happened was we got an x, we got a y. Together, they make one solution. And that solution is the coordinate 3, 4. All right. So also keep in mind you can check once you get an answer, an actual solution, you can check it pretty quickly and see if you got it correct or not. So 3, and then this would be negative 12. Yeah, that's negative 9. So it works out pretty good. All right, so the practice for this, I don't have written down. So anyway, I'll put that in Canvas, all right? And you can see what that practice is. Sorry about that. Well, anyway, thanks for watching. Have a good one.